What's on our agenda today? Yeah. What? No, what? Okay, so thank you. You got your partner in front here. Reviewing isotopes and then? Yeah? Spectroscope lab. All right, cool. So we're just going to maybe 20 minutes up here practicing a couple things. Thank you for most of you guys giving me some feedback on where you struggle on problem set 4. It'll give me a chance to highlight those main pieces, mainly the problems, the ones where you have to show your math on the board whenever I go over problem set. But if you don't practice or push yourself to challenge your thinking, you'll never go past where you are. You miss every shot you don't take, right? So take the shot, try it out, and then move on, right? If you get it wrong, you get it wrong, but at least you tried. If you don't give you any work, you're like, I didn't know where to start. That means you didn't go back and look at your notes. Because basically everything on problem set is from your notes or from a video or from something that we did in class. So try it for yourself, that way we can kind of work further together, okay? So explain the difference between a cation and an anion. Grant, give me something.
Cation positive.
It is a positive charged ion, okay? Cole, give me something else. Give me the opposite of a cation's charge. Negative. An anion is a negative ion, or it's a negatively charged ion. Kelsey, give me how a cation would be formed.
Electrons are taken away.
Right. So a cation has lost a certain number of electrons to overall give it a +1, +2, +3 charge, something like that. Will, tell me how an anion is formed.
Electrons are added.
Right, electrons are added or gained. Okay, so we know those are two different types of ions. What's the only subatomic particle that changed here? Electrons, right? When you're making a charged particle, you can only change electrons, and that's it. Everything else is inherently the same about those two ions, be it the neutrons and the protons. What subatomic particle always stays the same, Hallie?
We guessed on this, if you remember, neutron?
That one can vary to give us different masses for the same element.
Oh, it's proton because it's the same number as the atomic number.
Atomic number, yeah. All right, so the atomic number is what the periodic table says, and if I say potassium is atomic number 19, and I've changed that, I have totally changed the element's type. So I have to make sure that if I'm talking about one type of element, I keep the number of protons because it's like its identity. What type of atomic particle, we already answered that one, changes to make an ion? What was that, guys? Electron. And then which particle changes to incorporate a different idea about that element, meaning a different isotope? Izzy? Neutrons. All right, perfect. If you're thinking neutrons, you're thinking more about the isotope masses changing. If you're thinking about electrons, you're thinking about the same element, but it's of a different charge. Are you a little bit clear on subatomics? You all right? If I can get information out of you, I can not quiz you. That's kind of what I like to do sometimes, versus giving you quizzes, which makes me put you in a more stressful situation than I have to. Okay? So let's check problem set 4. Ready? And I'm just going to call up the true false first. The true false stuff is more of reading your textbook, so conceptual understanding, like the multiple choice side of the test. And a lot of you guys did better on your free response, which I'll give those back towards the end of class today. You did better on your free response than you did on your multiple choice because you practice your problem sets. If you practice your problem sets, the free response is easy peasy. If you copy your problem sets from somebody else, the free response will kick you in the butt. But the multiple choice side of things is more about reading the textbook, reading your reading guides really thoroughly, and then this true false section kind of gives you some guidance as well. So I'm going to start here, okay? 1, not true. 2, sometimes true. 3, always true. 4, not true. 5, always true. 6, not true. 7, always true. 8, not true. 9, always true. 10, always true. 11, always true. 12, not true. 13, always true. 14, always true. 15, not true. What's that?
So if we put sometimes true for 5, that's like not.
I said, the way it was phrased, it was always true, but I can't remember exactly how it was phrased, but if you're thinking of an ion, it would be sometimes true. I would take either, but the best answer was definitely always true. All right, going on to the matching here, okay? So number 1 is T, because some of my letters might be a little hard to read. What's up? Okay, give me a second, okay? Number 1, true, 2, I'm sorry, not true. 1 T, 2 S, 3 R, 4 P, 5 N, 6 O, 7 Q, 8 I, 9K, 10M, 11J, 12L, 13D, 14B, 15H, 16C, 17F, 18E, 19A, 20G. Question, Izzy?
Yeah, on number 5 it said atoms of elements electrical.
So that's the question I was just elaborating on for a second. So who is atomic number 5? Your table.
Boron.
Boron. Okay, so boron in its electrically neutral state, boron has 5 protons, 5 electrons, and I think it's like 10.81. So it's around up to 11. So 6 neutrons. Okay. So that's it in its electrically neutral state. The protons and electrons cancel each other out. That's why I said the way that was phrased is always true. Except when we say atom, I mean, God, everything's an atom, right? Everything. So it's not really specific. If you think of an ion form of this, let's call it boron 3 plus. What does it consist of now? 5 protons, good. 2 electrons, 6 neutrons still. So this is no longer electrically neutral because the protons and electrons don't cancel each other out. That's why I just elaborated on the word ion a little bit more there.
I think it's 6.
The mass of boron is, I think, 10.81. Yeah. I don't have, okay, so I rounded that up to 11 because you can't have a partial neutron. So I went to it for 11 to be the total mass. Subtract your protons to give you 6 neutrons. Good question. Yeah.
I switched 11 and 12.
That's just the definition of more about the atomic mass units. Because those are the questions, right? Those are eerily close. If you just read the question a bit more, it's 1/12 of a carbon atom. It's a weird definition. Memorize it. All right, questions here? Vocab stuff you just have to make sure you're aware of. So, oh man, did I show my math for these? What? Make sure that you're showing your stuff so I can give you feedback. So in terms, this is what I would expect for like a full credit response for your response. I like to show you what I expect so everything's really clear. So you're not like, how does she want me to show this? It's just to show me all your thoughts as you walk through things, okay? So you have your percentages, you back those up 2 decimals to give you, you have your percentages, you back those up 2 decimal points to give you the decimal format. Multiply by your masses, you get the individual pieces, and you add them together. So it should be about 16 AMUs, or 16 grams per mole sometimes is how we phrase it. So because of the lowest decimals were 2, you're going to go with the lowest decimals because this is an addition problem. So 16 should be your final mass. Thumbs up there. Okay. Never, ever, ever divide at the end, okay? For chlorine, similar story. You have your individual masses. Here, they were very specific, not just the 35 and the 37, but very specific. You take your forms of the decimal, or percent of the decimal, and then take your final products and add those up, so it'd be approximately 35.45. And I used more decimals because these had more digits to work with. So most of you guys looked like you were fine there. It was 3. What's up?
Did you ever need to like round it?
It depends on if this is like a multiple choice question, you'll round to the closest one. In terms of sig figs, this probably would be actually better at 3 decimals. So I can't remember if the last decimal was there. It may be 35.450. Was it 0? Okay. So I just didn't record it here, but it should be to a 3rd decimal point here.
Wait,
Yeah.
so how does the sig fig work? Like when do we use it? Like, because for the first one I put like 16.0 zeros and I put it back.
So look at the initial masses because this is basically just an addition problem. We're adding 2 masses together and that's it. So think of addition, we count decimals, the lowest decimal wins. The lowest decimal is how we record it. Because what we're multiplying by is a percent. Percents are not measurements, so we disregard them as in terms of like their sig figs. So this was why those having 3 decimals, this should have 3 decimals. All right, it looked like 3 though was the end all be all to our life here with isotopes. So you were given, from my work here, looks like you were given percents. This is a little scratched up. I scan these in and they don't always look really pretty at the end. But as you take your percent, and then you multiply them by the masses given, 27.97, 28, and 29 some change. Those are your masses. These are your percents of decimals again. Take them, add them up, get your final answer. It's the same thing over and over again. I gave you 3. Was that enough? Okay. And then let's quickly just check the subatomic one, which, oh, I didn't scan that one. I have it on my other one though. Hold on. So, I can't show you that right now. I'll show you that later, okay? Because it's not on my key right here. Okay, so who feels okay with isotopes and ions and subatomics? You know, like this, something. Give me some feedback here. Because if I can get feedback, I don't have to quiz you. So if nobody gives me feedback, it doesn't help a whole lot. Yeah. 2 or 3 from here. So let me tell you the gist of it. Okay, the gist is you're going to take, and I want somebody else to tell me the gist of this. You have your isotope, right? You have, let's say, number, like for example, number 2. You have 2 isotopes. Tell me what you're supposed to, your few steps you're supposed to take here. Austin, will you help me out there for number 2?
Just take the mass, 10%, and multiply.
Okay, so take the mass, and this was like 30. I'll use 35 AMUs just for simplicity's sake. So there's our mass, and there's our other mass. And
Take the percent, put it in decimal point.
so these percents will be given to you, right? So the 35% was actually given as 75.8, and the other one was given as 24.2. Okay, what do you mean as a decimal point?
Just move the decimal over to the left.
Okay, so we're basically dividing by what? 100, because all percents are based out of 100. So that's 0.758, and this is what? 0.242. And these individually, isotope 1, isotope 2, once we take their mass times their percent, what do we do with those? We add them up. So that's in the end kind of what we're doing. It's the same process over and over. 1, 2, and 3 were exactly the same question. Yeah, they were all just percents times their masses equivalently. Okay. All right, let's go past this though. Okay, I'm not going to do this right now. I'll come back to this if I need to. So we talked about light on Friday. Okay, turn to your partner. Tell them what you remember about the stuff we talked about Friday. Go.
I think it's just friends
There's this one
a photon as a bundle.
All right, pause. 3, 2, 1. Now answer these questions with your partner. Answer these questions with your partner. These are just talking about relationships. Is it a direct or indirect relationship? Inverse relationship, that kind of thing.
That's the direct. That's wavelength energy. Isn't it like no longer, not longer, but like.
We're going to take some notes after this, so it's probably a good start.
So that's direct.
Take 30 more seconds.
Those are the higher frequencies. It goes like that.
Take attendance robust. I would write this down because we're getting ready to take notes about this, so it's a good starting point. We're going to take maybe 10 minutes of notes. Please don't give me the, aw man, notes. It's going to be on light. It's about to get lit. Come on. That was good, guys. It's good. It's good. Just gotta take attendance real fast.
It's literally so hard.
Zoe sent me a meme on Twitter about the moles thing, and we need to show it to you.
It's really.
That's alright. My husband always responds to all my texts potassium.
Oh.
Okay.
Okay.
You always respond to his stuff?
No. Alright, we're gonna watch a video first, okay? Because I didn't get to show you guys this Friday.
Light is the connection between us and the universe. Through light, we can experience distant stars and look back at the beginning of existence itself. But what is light? In a nutshell, light is the smallest quantity of energy that can be transported. A photon, an elementary particle without a real size that can't be split, only created or destroyed. Light also has a wave-particle duality, being kind of a particle and a wave at the same time, although this is a lie. Also, when we say light, we actually mean visible light, which is a tiny part of the electromagnetic spectrum, energy in the form of electromagnetic radiation. Electromagnetic radiation consists of an enormous range of wavelengths and frequencies. Gamma rays have the smallest wavelengths because they're the highest energy photons. But most gamma rays are just under 10 picometers, which is still way smaller than a hydrogen atom. For reference, a hydrogen atom compared to a cent is about as big as a cent compared to the moon. Visible light is in the middle of the spectrum, in the range of about 400 nanometers to 700 nanometers, about the size of bacteria.
That's crazy.
On the other end of the spectrum, radio waves can be up to 100 kilometers in diameter, while the biggest wavelengths we know exist can span from 10,000 kilometers to a baffling 100,000 kilometers, way larger than Earth. From a physics standpoint, all these different waves are the same. They all have the wave-particle duality and travel at c, the speed of light, just at different frequencies. So what makes visible light special then? Well, absolutely nothing. We just happen to have evolved eyes that are good at registering exactly this part of the electromagnetic spectrum. This is not a complete coincidence, though. Visible light is the only set of electromagnetic radiation that propagates well in water, which happens to be where most eyes first evolved millions of years ago. That was a smart move because light not only interacts with matter, it's also altered by it and can be used to gather information about the world around us with almost no delay, which is arguably really helpful for survival. Okay, where does light come from? A vast range of electromagnetic waves are created when atoms or molecules drop from a higher state of energy to a lower one. They lose energy and emit it in the form of radiation. At the microscopic level, visible light is created when an electron within an atom, that is, in an excited state, drops to a lower energy state and loses this excess energy. The same way incoming light can elevate an electron to a higher state of energy by being absorbed by it. Macroscopically, the moving charge of the electron creates an oscillating magnet field, which creates an oscillating electric field perpendicular to it. These two fields move themselves through space, transferring energy from one place to another, carrying information about its place of creation with it. Why, of all the things in the universe, is light the fastest thing there is? Let's change the question. What is the fastest way to travel through space in the universe? It's c, exactly 299,792,458 meters per second in a vacuum. 1 billion kilometers per hour. Electromagnetic radiation just happens to move this fast. Any particle that has no mass travels at c, without acceleration or any in between. The light that's being released from a candle does not speed up until it reaches light speed. At the very instant of its creation, its speed is c. So why is c, or the speed of light, finite then? Well, nobody knows. Our universe is just built this way. We don't have a smart answer here. So light is a part of a spectrum, an elementary particle that also behaves like a wave, propelled by two perpendicular fields traveling at the speed limit of the universe. Okay, that's nice and all, but what about all the crazy stuff about traveling at the speed of light and time, the twin paradox, quantum stuff, and things like that? We have to save them for another video. For now, let's just be happy that we evolved eyes that pick up waves of information permeating the universe, making us see things that help us to put our existence into perspective.
All right, is everybody okay from that? You guys okay? right, anybody else have some other comments? So, what, some of those things are beyond us, right? They're above our pay grade. But I want you to be aware that there are things that you don't know. Like, how else are you supposed to know what you don't know if you don't know them? How are you supposed to know what you don't know if you don't know them?
I don't know.
I mean, that's the point. You have to let yourself become aware and be an aware citizen. One thing they did say, and I didn't mention this today, or I probably won't mention this again today, but this was the particle wave duality where they're like, there's this particle-like property that photons have, and there's a wave-like property that photons have. Just understand that duality needs two, and it has two separate types of properties. Light is a weird, weird thing. Electrons are weird, weird things, and they interact with matter in very particular ways. So we'll kind of talk about that a little bit more today, okay? So, wavelength and frequency, direct or indirect, guys?
Direct.
So let's review what the word direct means. Direct means positive correlation, and indirect means a negative correlation. So we've changed our answer. Why? Good. As wavelength gets higher, meaning longer, what happens to its frequency?
It goes down.
It gets really slow. Okay. As wavelength goes up, frequency goes down. And that's because they have to equal what when multiplied together? Speed of light. They have to equal those. They have no choice. Wavelength times frequency equals c. I can't change c. It is the speed limit of the universe. So as wavelength goes down and gets smaller, what happens to the wave or to the frequency? It gets higher, meaning it gets faster. Okay, so that's an indirect relationship. Coolio?
Yeah.
Moving on. Wavelength and energy. So think about how moving fast and moving slow correlates to energy. What do you guys say over there, Luke? Indirect. So long waves means what? So long waves, does that mean high energy or low energy? Low energy, good. Okay, so we have long waves, so as the wavelength goes up, the energy of that wave diminishes because it's really slow. So again, that's an indirect relationship. So understanding the conceptual correlations is important, and then we'll do the mathematical correlations as well. Frequency and energy. What do you guys say back there, Grant? This one is direct. So if it moves fast, what would you consider its energy to be? High or low? If it moves fast, high energy. So this is kind of conceptualizing it, but as it moves fast, what do I mean by that? I mean its frequency is what? High or low? High. A high frequency also means it's moving fast, which means it has a lot of energy. High frequency, high energy. So that's a direct relationship because as one elevates, the other one also elevates. As one diminishes, the other one also diminishes. So they move the same directions in terms of their mathematical relationships as well. They're messing with blenders and so forth. Okay. So these all come into play into our equations. The only equation we have not learned yet is the energy one. It plays off the one from Friday, which was what again? Okay, C is equal to wavelength times frequency. So here we go. We're going to do a couple calculations with this and then we'll be okay. I'll take a minute to let you write that down before I start explaining. Continue the tone from Friday. Continue to come here and keep that up. You guys decide to either streamline your notes online, if you can organize it on your printed ones, or streamline on your own paper. Note where things are picking up and not so that you can study them. I did print out some of the notes just so your writing is more about the problem solving process, which is why I said it's mine out here. Which has like Planck and Einstein, but not already. I'm going to calculate how. Okay. All right, so we went from way back in the day, Democritus, Aristotle. Who's next? John Dalton, and then for the longest time, J.J. Thomson, compounding model, Rutherford, the gold-full experiment. Chadwick was like, hey, there's neutrons. And then Bohr, he's like, ooh, look what I've done. But then it was just for hydrogen, right? So we figured out there's more to be done. So then Planck, Einstein, Schrodinger, Heisenberg, a bunch of other scientists got together. So, yeah, we're going to go a little farther than what Bohr did, and that's where this is starting to pick up. Yeah.
On an early question, you said on the science too.
Let me look on my calendar. Okay.
Okay.
Remind me in like 5 minutes. All right, so basically we saw that there were hot glowing solids, and those hot glowing solids had a different color, and those different colors correlated to different temperatures. So they said there must be a light correlation to temperature, or how fast the light's coming to us. So that's when we're correlating a little bit of the energy side of things to how fast the particles or the photons are traveling, but we didn't call that velocity. What do we call that? Frequency. So there must be a correlation between energy and frequency, and that's what this first part here says. So that correlation actually has its own equation. It's E is equal to HV. E is energy. Energy has to be established in joules, J for joules, and then V is what? Don't say velocity in this case. Let's go back to, we're correlating to what we learned previously. Frequency. We know it's velocity according to their theory of Planck's theory, but we're going to call it frequency because I want you to recognize the correlation between the two, Friday and the today. And then so Planck was like, well, what's the correlation between them? There's this constant. Well, of course, everybody's got to name something after themselves, so they're in the textbooks forever. Planck names the constant after himself because he's the one that made this connection. So 6.626 times 10 to the negative 34th joules times seconds. It's a combined unit, just like C was meters per second, speed of light, right? 3.00 times 10 to the 8th meters per second. This Planck's constant also has like a combined unit. So what is frequency measured in again? Say again. Look back at your notes. What is frequency measured in? You can say hertz, but it hurts me. It doesn't help me. I can't see the connection to those units. I'll wait on you guys. Look back at your notes. Yeah. Waves per second, or we just call that per second because we know we're talking about waves. So that's a per second, which we don't write like that. We write as like 1 over second, or second to the negative 1, something like that. Either way, what you'll notice is that in the end, we're doing E is equal to H times V. So that's E is equal to joule seconds. That's our H's constants units. And then we're multiplying it by V, which is per second. So I'm going to write that as here is per second. What cancels? Second, what remains? Joules. So you have to show your units for me to see that you're understanding how these pieces fit together. All right. So again, this is the equation that's the second equation that's connecting from wavelength and frequency to energy. Einstein did have a play in this too, and that's how he kind of came up with the theory of relativity. But we've already spoke of this just a brief amount about how a large explosion, like a nuclear decay event, is where we get a lot of energy, and that's correlated to just the tiniest amount of mass that would have been destroyed, as they say. But we generally say law of conservation of matter. Matter's neither been created nor destroyed. This is a very special case. Okay, and let's calculate. We're using these two equations. Follow me with no interruptions for the first one. Write down it with me, and then we'll move on to asking some questions from you guys, okay? So this is the one that I've written on your paper for you, but you need to write down the math as we go. A helium laser emits light at a wavelength of 633 nanometers. All right, that seems to be important. What variable is that? Wavelength, which we write as the upside down little y thing, right? 633 nanometers. Wavelength, 633 nanometers. What is the frequency of this light? Okay, what's the variable for frequency? Say again? V. Good, V. Okay, so that right now is our question. We have one given, we have a V that we're looking for. Which of these equations, the left one or the right one, am I going to have to use? The left one or the right one up here? Right one. It's the only one that has what and what in it. Frequency and wavelength, the two things in the question. So now that we've selected, so one is kind of right down your givens in your question. Two is to select the equation and then move on from there. Okay, so the equation is C is equal to lambda times frequency, or wavelength times frequency. Again, what is C before I move on? What is C? Give me that number.
3.00 times 10 to the 8.
10 to the 8 meters per second.
Yeah.
So before I move on from here, I want you, somebody raise their hand and tell me what is going to be causing me some trouble here in this problem. Raise your hand and tell me. Go for it, Mackenzie. Right, I have to convert to either meters or nanometers. I can't use them both. They're not going to cancel. So we always go with meters. Convert this guy to meters. Okay? So let's just do that to the side before we even approach the question. 633 nanometers. In your head or on your number line, come up with your conversion factor, which is your metric King Henry guide thing, okay? Raise your hand when you got me. Emma? Do you have it? Do you have the conversion? Or give me the conversion first.
10,000
Can you give me that in scientific notation?
10 times 10 to the 6.
Higher. You're missing. You got. I think you skipped your decimals. There's dots count. Somebody pick up from there.
You have
Yeah.
1 times 10 to the 9.
10 to the 9. It's 9 zeros or placeholders away from base. Count those, okay? So 10 to the 9th nanos are in 1 meter. 10 to the 9th nanometers, that's a billion. Nanometers are in 1 meter. 1 big meter, lots and lots and lots and lots and lots of little nanometers. So nanometers cancel, all right? So that's 6.33 times 10 to the negative 7th meters. That is your wavelength. 6.33 times 10 to the negative 7th meters. Because what are you mathematically doing? 633 divided by 10 to the 9th. That backs a decimal up 9 places, which, putting scientific notation, would be 10 to the negative 7. Okay. From here, you move on to find the frequency. I'm going to come around for questions. From here, move to find the frequency.
I just defined the equation here, and this is defining what C actually is. So you have so you can look at this This is going to come from you don't have a calculator, always grab one more just in case.
Alright guys, I goofed up. Some of my math is all hidden away here. Alright, look up here if you are done. Look up here if you're done. Okay, some of you are still working there. Okay. Continue on your paper. I'm gonna solve up here for some folks who are stuck. Alright, look back up here for me. Give me a thumbs up if you made it to the rearrangement of your light equation. You divided by wavelength, and you plugged it in. Because once you have your light equation, and you have the wavelength, that means you have the wavelength, okay, so you're good there. You know the constant speed of light. You can look back to your notes until you got that up here. So you know that. Your question is V. You're looking for V. You have to isolate that. So algebra, right? So take your equation, rearrange to isolate V by itself. So divide by your wavelength on both sides. Give me a thumbs up if you know how to do this. And now this is a different context, right? We're talking about the speed of light. Like, what the heck? But it's algebra. It all applies. Math crosses all disciplines. So we have our wavelength that cancels. Frequency is equal to C over lambda, or C over wavelength. So C over wavelength. C, 3.00 times 10 to the 8th meters per second. Wavelength, which we just got here with our units matching. Now we can cancel here, units-wise. Meters, leaving us with not just seconds, per seconds, okay? So 2.1-ish times 10 to the 14th. What is this? What is it? Or not 2, sorry, 5.4 point, okay. I'm trying to do this in my head. I was multiplying 4.74 times 10 to the 14th. Okay, if you didn't get times 10 to the 14th, it's because you have to put parentheses when you're dividing in your calculator, because it will think that you're dividing by 6.33, and then it'll think separate step multiply, but it doesn't understand that's one big step.
So what's the per
It's saying it's number of waves per second. But we just usually don't write waves because we're talking about waves as understood. Alright, that was stuff from Friday, not even new stuff. Now, I'm going to ignore this question that's kind of hanging here in the middle. Take the same information, now that we have the V, the frequency, and now I want you to find the energy of that wave. Okay? So find the energy of that wave. Guys, stop whining. Stop whining. First of all, you have the energy equation. You just wrote it down. You have the V, and you have the H. Go. Go back to look at the notes you just wrote down. What is H, guys? This is your equation, right? E is equal to HV. You just had that down from your notes previously. You're pulling all the information down. Everybody, what is H? 6.626 times 10 negative 34th units. Joules times seconds. This is a constant. It's called H, Planck's constant. You will be given that for a while, okay? V. Where do we get V from in all of our work? Well, we just calculated, right? So this is it. We're going to pull it down right here now. This is V. So it's very simple if you have your labels on your work and your units and everything. 4.74 times 10 to the 14th per second. What units cancel? Seconds, because we have a normal second on numerator and then a per second meaning in denominator. What unit remains? Joules, and guess what energy should be derived in? Joules. So calculate this in your calculator just by multiplying simply across. Any takers? E is equal to
3.14 times 10 to the negative.
-19 joules. That's a -19. There you go. So we take our wavelength and our frequency, we figure out whichever one we don't have, take our frequency, plug it into the energy equation, and get energy. So there's two equations, yeah.
So what is the 4.08 or 4.80 times 10 to the 17?
Where do you see 4.80? Oh, that I'm working this question. Yeah, so ignore the stuff in the background. It's not letting me move it for some reason. We were working the same question. I just was writing it on top of the screen. Okay, nope. We're going to get to another question shortly. I wanted to make sure you could follow the question. Okay? Yeah. This is called H. This is Planck's constant. Here to the top. Okay. Now, we're starting over. Let's do... Now I'm going to maybe erase a little bit. I want you guys to take this FM station. Ooh, thank you. Take this FM station, that's 98.5 megahertz. Okay, megahertz. And I want you to find the frequency and the energy. Go. You have hopefully just a couple minutes you need for that. I'm not sorry. I meant wavelength and energy. Thank you. Similar question. Not quite the same. Wavelength and energy. So remember where mega is on your scale? Do you remember that one? So it's 3 zeros ahead of K. So it's 1,000 times bigger than K.
So,
Dot M. Work with the person next to you, please. Raise your hand. Get the rest of the place.
you have to get hertz. And hertz is the first
Regular hertz.
Is it 9.85 10 to the 8 times 10 to the 8. You get 9.85 times 10 to the 8.
So if some of you guys are confused on the megahertz, I'll work it up here, but otherwise you guys keep doing your own thing. The mega is the 3 points away from kilo from the king. Henry died by drinking chocolate milk, da da da. So I have to get down to base. I have to get down to base first, so I gotta get from mega to base. So for me to do that, I need to take 98.5 megahertz and get out of megahertz. So megahertz is the largest unit, so I'm gonna put a 1 with that one. And I'm gonna get down to base, and I'll see that there's 6 0 difference there. So 1, 2, 3, 4, 5, 6. 10 to the 6 is what that means. And hertz is just our base unit of frequency, or per second as we normally call it. So that's 9.85 times 10 to the 7th hertz, aka per second. So this now is V. Now you should feel good about taking V to wavelength energy.
I got 197 over 600. .328 meters.
So this is it's like a separate thought. Yeah, frequency, which is in hertz or per second.
Look that. Divide that by 3.
But they're doing that in well, I got a completely different answer.
C equals 3.0 times 38.
No, I don't need to add 2 right now.
Divided by 9.5 times 10 to the 7. And that will give you the C is the length. Is 3.0.
You have to in parentheses or something.
Meters per second.
I think I typed the celebration. Yo, did you get 3.04? Yeah.
3.05. Yeah, 3.0.
3.06. What I got. Round it up if you're going to do something like that. 3.04569. So I rounded up.
I know what.
Oh, I see what you're saying. I went 4.5. My bad. 4.5. 4.5.
5, 6. For that one,
Un minuto, por favor.
we all need to answer.
Yes, H is a constant. H. It's the H constant. It's in your notes. Look right above where you're looking. H. Okay. All right, loves, look back up here for me. Let's track our work here. I'm going to start with wavelength. Give me a thumbs up if you think you got your wavelength correctly adapted in the approach. Okay, so I think the hardest part of this was that megahertz. I'm going to be honest, because if you know your two equations and you know how to plug a variable in and isolate one of them, it's all algebra. It's all algebra. So we're going to take our megahertz thing, which I helped you guys get to your V. Notice V's in both equations. You could have gone energy or you could have gone to wavelength first. Either way, it will work. So I went just to find the wavelength first. So C is equal to lambda times frequency divided by frequency on both sides. C over frequency is what you're going to plug in your calculator. C is a constant. You will write that in every single question. V is different, right? Because it's a different frequency for every wave we're working with. The per second and per second cancel, leaving us with a unit of wave or wavelength, which is meters. Who got approximately 3 meters? That's a pretty long wave, and that's like the megahertz I was telling you guys about the frequencies of the radio stations you listen to. Kind of cool. And then separate kind of thought, you're getting your energy. E is equal to HV. H is a constant. You will always know it. 6.626 times 10 to the negative 34th. Joules times seconds. So taking the same V you just used, plugging it in here, this is a per second unit. So the seconds and per second cancel to leave you with joules. What should energy be recorded in? Joules. And that's going to be, some energy. That's actually smaller than some of the other stuff, so it's a slow wave. Yeah.
Do we have to memorize?
You will accidentally memorize all these because you're going to do a bunch of problems with them. Yeah. Yeah.
So it's per second? Is it
Frequency is, yes. Okay. All right, so I feel like I went slow enough to give you the chance to kind of ask me some questions. Who has some more questions though right now that you guys might have before we move on? Who feels like after some practice they'll understand what they're doing? Okay, that's always the case with this. Trust me, it's not like a new case situation for that. 1 second, okay? So what my thought was that we'd actually get to our level earlier, but we have, I always forget time to get out, 48. Okay, we got about 25 minutes. So let me tell you the premise of it first, and I can still help some of you guys with some of this as we go. Basically, we like to look out into the night sky and see things far away. Well, how do we see things far away? Okay, but how is it coming to us? As light. Like they call it light years, right? See things that has traveled through the universe. So we have spectroscopes, which are those little things you guys were holding up and looking at the lights last week. So it's to see the fingerprint or the atomic fingerprint of the individual. I'll go back to this in a second. Of the individual matter that's out in the world. So spectroscopy is us looking out at the light that comes to us and then just analyzing it a little bit. So we're going to kind of do that as best we can with our spectroscopes. Now they're cheap, right? The little films will bend, so don't throw them around. The diffraction gratings in there are kind of fragile. And I don't have anything that's going to let us see this much, but like nebula and stuff. But we'll see some stuff out here, okay? So basically, the gist is I want you to get some hands-on experience with seeing the electrons move through the light sources we have in here. And then I have a little thing in the back that's a power source. I'm gonna electrocute some gases. So I want you guys to see that too, like a neon light, but we're gonna do it in front of your face. So I do need you guys to share, because I think I got about 25, and there's a little more than that in the room in terms of the spectroscopes. And as I call that groups to look at the electrocution source, then you guys kind of have to come in small groups because it's hard to see more than like 5 people wide. So I'll call you guys down for that. The light source, that's mercury, Hg. Mercury is above us. It's these fluorescent lights above us. All the other parts of the lab will say a frosted bulb. Well, you probably can't see it. If you turn around, there's a couple. There's a green frosted bulb back there. There's a yellow frosted bulb. There's a red frosted bulb. They're colorful lights. If it says incandescent or compact fluorescent light, you guys will have to find those. But there's different light sources at every station, so we will be moving around a lot. So you need to be cognizant of people moving around you. So the lab is very straightforward. I'll help you guys when we get back there. But this is the one thing you'll need to write down before we get back there, okay? Write down angstrom. Right, and you guys just pull a piece of paper for the lab and start on the top, okay? New piece of paper for your lab. Yeah, this will be a lab. You'll finish it. If we don't do it today, we can finish it during intervention. Yeah, let's see on the lab page. Second.
Most of it's on the lab.
I think it's probably beneficial just so you have that in front of you for the lab. So the angstrom is the SI units, System of International Measurement, preferred unit for light in terms of their wavelength. But you know what? We just immediately convert angstrom back to meter. So 1 angstrom is an A with a halo. 1 angstrom is equal to 1 times 10 to the negative 10th meters. Is that small or big? Pretty dang small, right? Like 10 to the negative 10th meters. It's a teeny, 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 tiny unit of measurement. So you can either think it as that, or, as you can see on the board, there's 2 ways to think about it. 1 big old meter is equal to 1 times 10 to the positive 10th angstroms. You do not have to memorize this. But what I want you to see is there, I've written it 2 different ways on the board, as on the board over there. So don't mix them up. 1 big angstrom is equal to a very, very, very small amount of meters. Or 1 big O meter equals a lot of angstroms. So that's what you're going to see in this spectroscope. What you're looking at in the spectroscope are lines, let's say like 7, 6, 5, 4, something like that. And the instructions are on the lab sheet. I think you have to take the line you see and multiply it by 1,000, and that will be the angstrom. Which from angstroms can you convert to meters? Using one of these, right? You can convert to meters. So the instructions are in the lab, but just note the line you see in there is not what it is. It actually is a little bit, gotta be a little bit modified. So I'll help you guys when we get back there. And your lab groups, which I try to keep you random. That is not your class. Okay, lab groups, here we go. Meaning back, let's go. You don't need glasses on. The lab stations are labeled. You can't find the lab station from the lab station 10 is here. Oh, 10 is here. Okay guys, so here's the deal. There's not one order that you have to do this lab in, because it's kind of a bunch of different pieces. So I'll have you guys go ahead and direct your attention to the one that says 1C. What is the wavelength of the orange band in the fluorescent tube or fluorescent bulb? So what you're going to do for that one is take the little slit, put it through the spectroscope, as many as you can at your station, okay? Sorry, that's a little bit. So the little slit is on your right side. The diffraction grating is on your left side. And you just look up, and I want you to tell me where that orange band is. Look at the orange band in the light source. You gotta look up at the light, up at the light source. Then that picture's a little lower. Okay. So I might have to stop you at some points, but I'm going to go ahead and ask that you guys listen. You can bounce around and do different parts of the lab, but you have to show your calculations for some of the things that are required. Everybody go ahead and plug up their light bulb. I'm going to cut the lights off in the classroom so you guys can utilize the light bulbs. Okay. And so some of us will have to move to different stations. If you have questions, let me know, okay? Oh yeah, this. It should be at the top of the lab sheet too, Grant.